Chapter 9, Section 3, Lesson 1, the Integral Test and P-Series. Our objectives are 1 and 2, which are from Chapter 8 about improper integrals, and then 3 and 4, which are relevant to Chapter 9, Section 3. We have to do 1 and 2 first so that you'll have the prerequisite knowledge to be able to do the integral test. So objectives 1 and 2 are from Chapter 8. So objective 1, you'll recognize that this is one type of an improper integral. It's one type. There are other types, but this is one type of an improper integral, and when we get to it, you'll see what we mean by that when we look at the definition of improper integrals. And of course, we will also relate this back to what you already know from Calculus AB about indefinite integrals and definite integrals. You will know how to determine whether an improper integral converges or diverges, and then we'll come to objectives 3 and 4, which are about series. Objective 3, you will know when you can use the integral test and what it can be used for. So you can't use it for any series. There are certain conditions that have to be satisfied for you to be able to use the integral test. And you'll be able to use the integral test. To review some Calculus AB content, what we have here is an indefinite integral. There are no limits of integration. And when you're finding an indefinite integral, you're looking for a family of antiderivatives. What you have here is a definite integral. There are limits of integration. When you are finding a definite integral, you're finding a numerical value. You can interpret it as the area between the x-axis and the graph of the integrand on the interval from x is equal to 1 to x is equal to 2. And we, of course, find a definite integral using the fundamental theorem of calculus, which requires you to find an antiderivative of the integrand and then evaluate it at the upper and lower limits of integration. So now let's look at number 1. This is an indefinite integral. How do you find this indefinite integral? There is an integration technique that you learned in Calculus AB, and it is called integration by substitution. So that's what we're going to do for number 1. So you use the u substitution, let u be equal to x squared plus 1. As a student asked earlier in response to for homework problems from the previous section about how do you know when you should do what particular technique? The same type of reasoning applies to finding integrals. You've learned different techniques, but how do you know which technique should be applied to a particular problem? You would know based on your experience about what tends to work for particular types of integrands. So here, integration by substitution tends to work well. And the reason for that is as follows. So why does this particular substitution work out pretty well for number 1? Because it allows us to change variables so that after changing variables, we get an indefinite integral whose antiderivative is known to us. So the purpose of doing integration by substitution is to take a particular problem and rewrite it in such a way that allows us to find the antiderivative, knowing our list of antiderivatives from Calculus AB. So the particular substitution that was suggested for this problem works out really well. You would let u be the denominator of the integrand, and you have to find what we call the differential of u. How do you find the differential of u? You take the derivative of x squared plus 1, which would be 2x, and then you multiply by the differential of x, which is dx. So that's great, but how does that help us change variables? So this is called our substitution, but we use all of this to change variables from integration with respect to x to integration with respect to u. So how do we do the change of variables step? You have to basically try to rewrite everything that's in terms of x to everything that's in terms of u using our substitution. So it's easy enough to replace the denominator with u because x squared plus 1 is equal to u. So we've got that. But if you look over here, we have x dx. And you have du is equal to 2 times x dx. So if you divide both sides of that equation by 2, you have du over 2 is equal to x dx. So I am able to replace x dx with du over 2. But I still have a 1 in the numerator. So you need to have a factor of 1 in the numerator. And if you have an indefinite integral, you're able to factor out constants from the integrand. The 1/2 here is a constant, so we can factor it out. And this is what we have. This is called the change of variables step. Why is what we have now better than what we had at the beginning? It's better because what we have here is better because we are able to determine what the antiderivative is from what we know from calculus AB. If your integrand is 1 over u, then the antiderivative would be the natural log of the absolute value of u. So you have 1/2 times the natural log of the absolute value of u plus the constant of integration c. So you can replace u with x squared plus 1. And now we have an antiderivative for our original problem. So that's what you do when you're looking for antiderivatives. So this is a family of antiderivatives. So if you were to take the derivative here, you would get the integrand that we had for number 1. So that's what you do with indefinite integrals. What do you do with definite integrals like we have for number 2? Here's what you do. You need to use the fundamental theorem of calculus, which means you're going to go ahead and find an antiderivative of the integrand, and you're going to write the antiderivative here, and you're going to evaluate the antiderivative at the upper and lower limits of integration and subtract. When you do that, the definite integral is equal to 1/2 times the natural log of 5 minus 1/2 times the natural log of 2. Having reviewed indefinite integrals and definite integrals, we are now ready to take a look at objective 1. What is an improper integral? And you will recognize this particular type as being one type of an improper integral, and you will know how to determine whether an improper integral converges or diverges. So we've looked at indefinite integrals and definite integrals in calculus AB, and now we're going to look at an improper integral. They are different types, and there's actually a whole other category of improper integrals that is not included in this definition. There are two main subtypes of improper integrals. This is the 3 cases in one of those subtypes. Today we're only going to focus on case 1 of this subtype of improper integrals. In this subtype of improper integrals, one of the limits of integration is infinity or negative infinity, or possibly both of the limits of integration are negative infinity and infinity. So that's one subtype of improper integral you could have, and we're going to look at case 1. So that's all we have to do for today, because this is all we need for the integral test, and we will come back to this section later to learn about other types. So if f, and f is referring to the integrand, if f is continuous on the interval from a to infinity, then this is an improper integral with an infinite limit of integration. And furthermore, this definition also tells us how we should deal with such an improper integral. You rewrite it as a definite integral from a to b. And then you take the limit of that definite integral as the upper limit of integration b approaches infinity. So that's how we deal with it. And in the first two cases, and we're looking at case 1, we say the improper integral converges if this limit here exists. And we say the improper integral diverges if the limit there does not exist. And we don't need to worry about the third case. In the third case, the improper integral on the left diverges if either of the improper integrals on the right diverges. So let's go ahead and take a look at an improper integral using the definition that we just saw. So what we're looking at here is an improper integral. And why is that an improper integral? Because the upper limit of integration is infinity. You will notice for this improper integral that the integrand is the same as the integrands that you worked with in the activity. The only difference was that in the activity, in number 1, although you had the same integrand, you had an indefinite integral. There were no limits of integration, and you were finding an antiderivative. And in number 2, although you had the same integrand, you had a definite integral because there were limits of integration. So in fact, from the activity, we already know what the antiderivative should be. So we're just going to take our work from the activity and substitute that into what we're going to do with the improper integral to determine whether it converges or diverges. And of course, the antiderivative is 1/2 times the natural log of the absolute value of x squared plus 1. So coming back to our improper integral, how do we determine if this improper integral converges or diverges? That's our question. And the definition of improper integral states the following. Here's how you determine if the improper integral converges or diverges. You're going to see if this limit exists or does not exist. If the limit exists, we say the improper integral converges. If the limit does not exist, we say the improper integral diverges. So using this definition, here's how we deal with the improper integral. We're going to write it as the limit of the definite integral from 1 to b, and the integrand is x over x squared plus 1 dx. And we're going to take the limit of this definite integral as the upper limit of integration b approaches infinity. And of course, we're able to do that using the antiderivative that we found in our activity that we started the lesson with. The antiderivative that we found was 1/2 times the natural log of the absolute value of x squared plus 1. And how do you work with a definite integral? You use the fundamental theorem of calculus. So you're going to write b for your upper limit of integration and 1 for your lower limit of integration. And using the fundamental theorem of calculus, we may write the following. The definite integral is going to be 1/2 times the natural log of the absolute value of x squared plus 1. I replace x with b, so I have the absolute value of b squared plus 1, minus 1/2 times the natural log of the absolute value of x squared plus 1. So I replace x with 1. 1 squared is 1. 1 plus 1 is 2. So this is what we have. So now we need to evaluate the limit that we see here and see if the limit exists. And if the limit exists, we say the improper integral converges. If the limit does not exist, we say the improper integral diverges. So what happens as b approaches infinity? Well, you have natural log of b squared plus 1. if b is approaching infinity, b squared will approach infinity. And when the argument for the natural log function approaches infinity, the natural log function will also approach infinity. And you can go back to the graph of the natural log function to understand that. It looks something like this, and as x approaches infinity, y is approaching infinity. So as the argument for the logarithm approaches infinity, the natural log will approach infinity. So this is a constant, but this term will go to infinity, so the limit does not exist. The limit does not exist. And because the limit does not exist, we say this improper integral diverges. This improper integral diverges. We'll end this part of the lesson by looking at an example of an improper integral that converges. So here we have an improper integral, and we want to know if it converges or diverges. So using the definition, we're going to write this as a definite integral. And we're going to take the limit of this definite integral as the upper limit of integration approaches infinity. The antiderivative here is going to be negative 1 times e to the negative x. You can do a formal u substitution, or you can get this mentally, and you can verify that this is correct by taking the derivative here, and you will get the integrand back. So now, to complete the work, we're going to go ahead and take the limit as b approaches infinity of this quantity, and of course we're using the fundamental theorem of calculus here. So we have negative 1 times e to the negative b minus negative 1 times e to the negative 0. And we're going to bring that work up here, and we have the limit as b approaches infinity of, we can write this quantity here as negative 1 over e to the b power. You can take this e to the negative b, and using properties of exponents, if you have a negative exponent in the numerator, you can take that to the denominator. And then you have minus negative e to the 0. So minus negative is plus, e to the 0 is 1. So what happens as b approaches infinity? As b approaches infinity, e to the b will also go to infinity. So this quantity here, negative 1 over e to the b, will go to 0. So the limit here is going to be equal to 0 plus 1, or 1. So because the limit exists, by definition, we say this improper integral converges, by definition. So this improper integral converges because the limit from the definition exists. So that brings us back to our objectives, and what we've done so far are objectives 1 and 2. We are able to recognize that this is one type of an improper integral, and we now know how to determine whether that particular type of integral, that particular type of improper integral converges or diverges. And now we're going to look at section 9.2 and look at objectives 3 and 4. You will know when you can use the integral test and what it can be used for, and you will be able to use the integral test. So here we have Theorem 9.10, the integral test, and it states the following. So here we have an infinite series. And what's the relationship between this improper integral and this infinite series? The integrand for the improper integral is f of x. And look at this here. F of x is the same rule that we have for the nth term in our infinite series. So that's what that states. So if you have a function f of x for the integrand in the improper integral, that is the same rule, the same function rule as the nth term of our infinite series. And furthermore, if this function f of x is positive, continuous, and decreasing for x greater than or equal to 1, or it could be some other number like 4 or 5 or 6, and the rules are the same, then either both the infinite series and the improper integral will converge, or both will diverge. So to determine, using the integral test, whether an infinite series converges or diverges, you can look at the corresponding improper integral and use what we learned about improper integrals to determine if the improper integral converges or diverges, and the series will do the same. If the improper integral converges, the series will converge, and if it diverges, the series will diverge. Although we will not look at the proof of the theorem for the integral test, it is provided in your textbook on page 617. And if you would like to look at the proof and try to understand it, I will refer you to a couple of things that we've learned in prior sections that is used to prove the integral test. So whenever you want to prove that a series converges or diverges, you have to use the definition of convergent and divergent series. So in the proof of the integral test, the definition of convergent and divergent series is used because that's what you have to use to show that a series converges or diverges. And of course, in the definition of convergent and divergent series, basically we look to see if the sequence of partial sums of the infinite series converges, and if it does, then we say the series converges. So to show that an infinite series converges, you have to consider the sequence of partial sums. And then in the proof of the integral test, you can see towards the end that how do we show that the sequence of partial sums converges? We actually rely on something that we learned in section 9.1, that if a sequence is bounded and monotonic, then it converges. So in the proof of the integral test, we're making the argument that the sequence of partial sums is both bounded and monotonic, and therefore the sequence of partial sums must converge by theorem 9.5. And if the sequence of partial sums converges, then by definition the series converges. That's basically how the proof is done. Of course, there are some other technical setup that you have to do prior to getting to the part that I highlighted, and you can look at that technical setup on page 617. But once you've established the integral test, you no longer have to worry about the definition of convergent and divergent series. It was used to establish the integral test, so now you can just go ahead and use it. But in the proof of the integral test, we use these conditions that f is positive, continuous, and decreasing, and therefore the integral test is only applicable if you have the integrand be positive, continuous, and decreasing. So those are the only instances in which the integral test can be used. So we just talked about the integral test and how we establish the truth of it, or how we prove it, and of course you have to look at the details on page 617, but we talked about the general idea. And you will know when you can use the integral test. We mentioned that just now. And what it can be used for. It can be used to determine whether an infinite series converges or diverges under certain conditions. And we will look at examples for using the integral test. So before we do that, we want to take a couple of minutes to discuss where we are in our study of series. So in section 9.2, we began by studying the definition of convergent and divergent series. We learned that a series converges if its sequence of partial sums converges. And then we looked at telescoping series. A telescoping series converges if its sequence of partial sums converges. So we're using the definition of a convergent series to determine if a telescoping series converges. We wrote a formula for its nth partial sum, and we took the limit of the nth partial sum as n approaches infinity, and if that limit existed, then by definition the telescoping series converges. And then we looked at geometric series. If we have a geometric series, first you have to be able to identify that you have a geometric series, and then it's pretty easy to know if a geometric series converges or diverges by looking at the absolute value of the common ratio. And of course, the proof of the theorem for the geometric series test goes back to this definition. Just like the proof of the integral test goes back to the definition. But once you have a theorem established, you no longer have to go back to the definition, you can just use the theorem. And then we looked at something called the nth term test for divergence. You can only use that to conclude that a series diverges if the limit of the nth term as n approaches infinity is not equal to 0. And today we're learning a new test called the integral test, which can only be used in certain situations. So now we'd like to take a look at a couple of examples about the integral test. And definitely we want to understand when we can use the integral test. We can use it to determine whether a series converges or diverges. And we want to be able to use it. So we want to take a look at example 1 from section 9.3 using the integral test. And the instructions are apply the integral test to this series. So look at the integral test. It states that to determine if an infinite series converges or diverges, you can examine the convergence or divergence of the improper integral whose integrand has the same rule as the nth term for the infinite series. So let's see if we can write an improper integral that has the same rule as the nth term for the given series. So we're going to write the improper integral, and we're going to start with n is equal to 1. So we have from 1 to infinity, and we're going to have the same rule as the nth term for the infinite series. So the rule for the nth term of the infinite series is n over n squared plus 1. So the integrand will be x over x squared plus 1 dx. So the integral test states that if this function is positive, continuous, and decreasing for x greater than or equal to 1, or possibly some other integer, then the integral test applies. And if the integral test does apply, and you are able to determine that the improper integral converges, then the series must converge. On the other hand, if the improper integral diverges, then the series must diverge. So let's first verify that the integral test can be used. So you have to look at the function f of x is equal to x over x squared plus 1. And you have to verify that this function will be positive, continuous, and decreasing for x greater than or equal to 1. For x greater than or equal to 1, you can see that the numerator of the function will be positive and the denominator of the function will be positive. So yes, for x greater than or equal to 1, a positive number divided by positive number is positive. So f of x will be positive. It'll be greater than 0. So that verifies the first requirement. And for x greater than or equal to 1, is the function continuous? The function f of x is a rational function, and rational functions are continuous on their domains. That's something that we learned from calculus AB. So you can just think about that and make that note. So you can say for x greater than or equal to 1, f of x is continuous. And then finally, you have to check to see if f of x is decreasing. And to do that, you're going to use calculus. You're going to check the sign of the first derivative of the function to see if the first derivative on the interval from 1 to infinity is negative, because if the first derivative is negative on an interval, the function is decreasing on that interval. That's also something from calculus AB. We learned that in chapter 3, the test for increasing and decreasing functions. So you can see that work done here in the example. So we're going to go ahead and find the derivative of f of x using the quotient rule. And when you simplify the derivative, this is what we have. And now we need to determine that the derivative is negative for x greater than 1. And because if that's the case, then by the test for decreasing functions, the function must be decreasing for x greater than 1, which would satisfy the requirements of the integral test for the function f. So how do you know that this derivative is going to be negative when x is greater than 1? Well, if you look at the denominator of the derivative, you have x squared plus 1 squared. So the denominator is always going to be positive because you're squaring x squared plus 1. Now if you look at the numerator, you have negative 1 times x squared plus 1. And for any x greater than 1, when you square it, you'll get a positive number, but then you multiply it by negative 1, so negative x squared will be negative. And because you're starting with x is equal to 1, for any value of x greater than 1, the magnitude of negative x squared will be greater than 1. So when you add a negative number whose magnitude is greater than 1 to positive 1, the numerator will be negative. And because the numerator is negative and the denominator is positive, the quotient, or the quotient, which is of course the derivative, will be negative. And because the derivative is negative, the function f is increasing. Is decreasing. The derivative is negative, so the function f is decreasing on the interval from 1 to infinity. So that verifies that the function f in the integrand of our improper integral is positive, continuous, and decreasing for x greater than or equal to 1. It's okay that we have an open interval starting at 1, not including 1. That doesn't matter. And in fact, the integer here could be some other integer such as 2, 3, 4, or 5. So now that we have verified that the integral test applies to our problem, we need to go ahead and use the integral test. And all the integral test states is this. If the improper integral converges, then the series will converge. If the improper integral diverges, then the series will diverge. Of course, you should remember that this particular improper integral is something that we've already worked with in the earlier part of the lesson. And in fact, it's the same integrand that you had for the beginning activity for this lesson. So you found that the antiderivative was 1/2 times the natural log of the absolute value of x squared plus 1. And we saw that this particular improper integral will diverge because as b goes to infinity, b squared will go to infinity, so the argument of the logarithm will go to infinity and natural log will go to infinity. So this limit does not exist, and because the limit does not exist, the improper integral diverges by definition. If the limit exists for the improper integral, we say it converges. If the limit does not exist, we say it diverges. So we had already done this work, and that's what you see here in example 1. And because the improper integral diverges, by the integral test, the series diverges. So now we want to take a look at example 2. Example 2 shows an infinite series. And so can we use the integral test? So you begin by writing the corresponding improper integral from 1 to infinity, and the rule for the integrand must match the rule for the nth term in our infinite series. So we have 1 over x squared plus 1 dx. And basically we need to begin by making sure that the integrand is a function that is positive, continuous, and decreasing for x greater than or equal to 1, or some other integer. And of course, the integrand already has the same rule as the nth term of our infinite series. So you can verify that all three conditions are satisfied. And in fact, in the textbook, it states that they are, but you have to check it on your own. And we will not check it together, but you can check it on your own if you like. And then you should check to make sure that it is applicable. But in this case, it is pre-made to be applicable. So we will skip that part just because it's already been done for us. But you can check to verify. And then you have to basically determine whether this improper integral converges or diverges. And if it converges, the series converges. If it diverges, the series diverges. So again, how do you determine whether this improper integral converges or diverges? You use the definition that we learned earlier in the lesson about improper integrals. Here's how you deal with it. You replace the upper limit of integration with, you replace it with b, and then you take the limit of the definite integral here as b goes to infinity. So how do you find an antiderivative for this integrand? You may remember an integration rule from calculus AB, and the antiderivative for this integrand is the arctangent of x. So using that, we have our antiderivative, which we will evaluate at the upper and lower limits of integration. So we have arctangent of b minus arctangent of 1, and you take the limit of that as b goes to infinity. So if you remember something about the tangent function, the tangent of pi over 2 is undefined. But as the angles approach pi over 2 from values that are less than pi over 2, the tangent function goes to infinity. So for the arctangent, if b is going to infinity, the arctangent will approach pi over 2. So because so we talked about that, and you can look at the graph of the tangent function to understand why that's the case. And then the arctangent of 1 is equal to pi over 4 because tangent of pi over 4 is equal to 1. So the improper integral converges because this limit exists. And therefore, by the integral test, the infinite series must also converge. So we just looked at objectives 3 and 4. You will know when you can use the integral test and what it can be used for, and you will know how to use the integral test. So some vocabulary. So we want to look at some vocabulary from today. I'll just go ahead and box the vocabulary that we have in our objectives. Of course, the integral test is vocabulary. Improper integral is vocabulary. An improper integral converging or diverging, and that's the main vocabulary from today: improper integral and integral test. And we began our lesson by looking at what an improper integral is and how to determine if an improper integral converges or diverges.